do have the prime speaking spot right before lunch, so unfortunately I'm going to have to try and Micro Machines guy this talk because it's actually really long, and I'm sure you'd all be very excited if this thing, started running through lunch. So let's get started. I'm going to skip a lot of the jokes and warm up and things that I normally do. And I'm just going to say that thank you for having me here at RubyConf. I am from Portland, Oregon. I used to live here in Kansas City. I used to work at Cerner, which I think half the people in this room used to work at Cerner. So no surprise there. I currently work for Mongo HQ, which is, if any of you have ever used Heroku and have used Mongo with Heroku, chances are you've run across Mongo HQ because we're the database as a service providers. I'm also coming out with a book very soon called 7 Databases in 7 Weeks. And if any of you are at RailsConf, I think I said the same thing. And I'm like, oh, it's coming out at the end of the summer, but it turns out writing a book is a much more arduous process than one would think. So, but it is coming out in beta November 30th, so look for that. So the thing that I wanted to talk about is just sort of a overarching view. We've only got about 30 minutes to go over this, and unfortunately, it's not one of those topics that's best condensed in such a small thing in the level of detail that I would really love to go over, especially considering that this is a Ruby conference. There's going to be some Ruby code, and I will make this as Ruby-centric as possible, but more importantly, I want everybody, hopefully, to be able to walk away with at least a good sort of 30,000-foot understanding of a lot of the things that are going on in the database world right now, and there are copious amounts. And if you've ever listened to or read anything about the NoSQL databases, you'll sort of hear the big four: graph databases, columnar databases, key value or document data store. That's fine, but then I enjoy throwing in relational, so there's really 5, because let's not forget the databases that all of us have been using for the past 40 years. So real quick, just talk about the ecosystem. And this map, I think, is a great example of why it's easy to get lost in the databases that are out there. And this is by far, in a way, not comprehensive. But it does a really good job of breaking down sort of the groupings and the classifications of databases that are out there. We're going to cover these. And there's several reasons. The ones that are in orange are the open source database. So I only really want to talk about the open source databases. There's several closed source ones out there. There's ones that are specifically only as a service, like App Engine and Amazon RDS and things like that. And those are fine, but let's stick with the code that we can read. So just a quick history on these databases. This is sort of a map of the ones that we're pretty much going to cover. If you notice at the very top, you zoom in, it kind of started around 2006, this whole big sort of database movement. I mean, up until that point, things were more or less relational databases were king. So it is still a really new modern thing. And if you look up there at the very top, this is a Google project called Megastore. And it is just out like now. I mean, it's only internal to Google, but there's new databases that are popping up. Voldemort, Redis, those things really only came around in 2009, and it's amazing in the past 2 years how they've become almost considered standard, which is a pretty amazing thing for an industry that has more or less been stagnant for the past 40 years. So I should notice it up at the top. It has a little corner. It says like Bigtables. Down at the bottom it says key value. And these are grouped in a different type. Bigtable is the Google implementation that a lot of these databases like HBase and Hypertable and Cassandra have spawned off of. We like to call them columnar data stores because of the way they store data, and I'll explain why for that nomenclature. Document data stores, all the big ones that people are probably aware of: Couch, DB, Mongo, Mongo HQ, as a provider that spawned off of that, Mongo Machines, another one, Mongo Labs, all of that. And then Graph Datastore. There's several out there. GraphDB and Neo4j, in my opinion, are pretty much the only ones worth looking at. There's other ones like Twitter has their own called FlockDB that, unless you're Twitter, I don't think you're going to find much use for it. So these are the selections of the databases we're going to cover. So let's start with the relational models. Here's a few of the open source relational databases. Postgres, MySQL. I mean, you're pretty much familiar with most of these, almost anyone in this room. And by the way, if I'm going too fast, I am going to have these slides available for download, so you don't need to be scribbling to write these down. But these are a lot of the really good Ruby drivers that I would recommend if you're using any of these databases. The difference, a lot of people are saying, well, why would you use Postgres over MySQL? I mean, this is a fight that's been going on for 15 years now. The way that I like to split them up is that Postgres is fine. Postgres is fantastic if you want sort of an academically focused database. If you want a database that sort of came from the world of database research, not as interested in speed as much as correctness. And I'm not saying it's slow at all, but like Postgres is very much about being modular and being able to plug in. If you're familiar with database indexing at all, you can write your own custom indexes on their framework called GIS, which is a generalized index search tree index. This is something that MySQL was not concerned with at all from the very beginning. They, again, as all open source projects go over time, they're sort of reaching a parity, so there's not a huge difference between them, but the groups of people are very different, and as we all know, the community is actually, can be very important. MySQL is what I recommend if you want something lighter, if you don't need a lot of the details that Postgres provides, like for the example, like if you're not writing your own custom indexing and writing your own really custom data structures and all of that, MySQL is fantastic. Drizzle split off of MySQL project. I guess there was some political or technical reasons. I'm not entirely sure why they split off, but it's a lighter version of MySQL. VoltDB is a relative newcomer in this relational database space, and it's really focused on scalability. I mean, it has a lot of built-in support for like auto sharding and things like this, so you can distribute your relational database out. One thing, and this is just a note, just because of the crowd, that I like to say, don't get obsessed with this whole ORM thing. The whole object relational mapper is fantastic. I mean, I love Active Record. I love AREL. I love AREL. One of the problems is this can get to be almost a little religious in the fact that the idea that you can't write SQL in code is just absurd. SQL is a fantastic language, and I think one of the best arguments for why it's fantastic is it's been around for ages and relatively unchanged. I mean, it's actually one of the longest, oldest languages that is still actively used all of the time. And it's because it's a very powerful mechanism for querying and deciphering data. And I got an argument with someone at RailsConf about this kind of query, how you could definitely write an AREL wrapper around these functions. And I'm like, but to what point? It doesn't make it any more portable because these functions only work in Postgres. And beyond that, it doesn't really make it any clearer than this. I mean, okay, this might, if you're not a SQL person, this might not be clear, but that's sort of a bunk argument because I could look at any language that I don't know and say, oh, yeah, this doesn't make any sense just because I don't know it. But what this does is finds the shortest distance object within a bounding cube in three-dimensional space, which, all right. That actually makes me really excited. But But I used to do research in high-dimensional database indexing. So, but that's all I'm really going to say about relational databases because it's something we all know pretty well. Bigtable, Columnar / Columnar data stores, HBase, Hypertable, Cassandra. Cassandra is sort of a weird little anomaly here, but it is technically a column-based data store. HBase is what I would say is probably the most true to the Bigtable concept. Bigtable is, if you're not familiar, the data store that Google invented about 10 years ago in order to deal with their massive amount of data that they have. And here are some good drivers to use. I find Stargate hit or miss because it goes through the REST interface. And if you're doing Bigtable, you're really looking for sort of these massively scalable, high throughput systems. So I actually recommend using Thrift. And I believe Thrift was a project created by Facebook. The neat thing about Thrift is that all of these column-oriented data stores have Thrift interfaces. So you can, in a very real sense, so Thrift is almost sort of like an ORM for column-oriented data stores, so that you can, write your little Thrift-based code and write your Thrift-based hooks, and there's a lot of similarity between them. Hypertable is kind of neat because it's got this little HQL, so it's a lot more queryable. I don't think that it's community. It's sort of, has corporate-backed things. It doesn't have sort of the mind share that HBase does. HBase is a Java-based project, though, and that does rub some people the wrong way. Cassandra is a hybrid, and I'll explain what that means when we get on to talking about React. But in a nutshell, I guess I'll just explain it right now, is that there was another big data store created by Amazon called Dynamo, and Cassandra sort of took the architecture of Dynamo and it took the column-oriented interface of Bigtable and mashed them together. And this was created by Facebook, and they thought this was a fantastic idea until they started having problems with the architecture. So they're actually moving a lot of their code, especially like their messaging system and everything, over to HBase. I don't not recommend Cassandra because unless you're Facebook scale or something, you're probably not going to run into the problems that they have. But I'm more of the mind of if you want to use Dynamo Data Store, use something like React. If you want to use a column-oriented data store, use something like HBase. I don't understand the point of the hybrid at all. So when I'm talking about columns, though, I keep throwing out these terms, and I know they get confusing, especially if you're from a relational world where columns mean something and rows mean something. Column-oriented data store, rather than in a table in a relational database where you might have a person table and then you have a name and a social security number, and then they're all stored together, they're clumped together in rows. Column-oriented storage flips it on its head and it actually stores data in columns. Now you might say, well, what's the point of this? There's actually several benefits to this. One of the big ones is the fact that if you have multiple data centers and you have multiple systems, you can actually even put columns, in subsystems that are dedicated to being optimized for dealing with that sort of data. Think about it in terms of Google, because they created it, where they have this giant data store that is dealing with scanning web pages and things like that, where you might have one column dedicated to holding the titles of a page and another column dedicated to versioning all of the details of a page. You might want those in two sort of different contexts, because the title of the page won't change very often, whereas the contents of the page might change very often. And so it sort of has this built-in version control. So a row is sort of an amorphous thing where you say, okay, give me the most recent version of the title, and then give me this version of the page body, and then it clumps them all together, and then that is sort of a row. But the nice thing is that all these column-oriented data stores have this built-in version control thing. I highly recommend using for something like a wiki. And here's some Ruby code. I'm not going to go over too much about it, but you can tell by this Apache, line 3 included Apache, Hadoop, HBase, Thrift. This was created by Java people. So you sort of got this, nested namespace. But I'm going to have this code available too, but this is just a real simple wrapper so that you can then execute code within Thrift and it connects to the server. This was a wiki, but you still need to do migrations in the same way that you would do migrations for a relational database. Here is just replicating all, where you have the scanner and it opens up. And the thing about a column-oriented data store, I should also mention, is the fact that all the keys are in order. So it's really fantastic for doing anything that you need to scan data. Again, it makes sense in a search engine like Google because they key everything in reverse nomenclature URLs. So you'll have com.google.maps, which is right beside com.google.www and com.google.zzz, whatever. And so they're in order. So if they just say, okay, well, give me all of the data about com.google, you can easily just start at the beginning and then just start scanning. And then once Google's done, you stop scanning. Implementation. Here's a way to get historical versions because, as I said, it has this built-in version control, and you can set timeouts on these versions as well and say, okay, I only want this data to live for this amount of time, or say I only want to store the last 5 records. So use Thrift; they all implement. I think we covered some of the H-based benefits. Cassandra has some benefits. It's configurable because of its architecture to be as consistent or available as you want, and I'll talk about that when we get to this sort of Dynamo style. Document Datastore. If any of you have ever used NoSQL database, it's probably going to be Document Datastore. It probably have been MongoDB or CouchDB. There's another one called RavenDB. I got to say, if any of you are aware of a Ruby driver for RavenDB, that would be fantastic because I could not find one. One thing that should be mentioned, though, is that RubyDB is written in .NET. So I think that's part of the reason it hasn't sort of gotten very popular in this sort of community. But I imagine it's a pretty fantastic data store. Mongo and Couch, though, is what we'll talk about. If you're not familiar, this is a document. Unlike the previous two we saw, unlike relational and like column-oriented data store, you don't migrate anything with document data store. You just stick values in. Now, you might wonder what the value of that. That makes a lot of people uncomfortable. The idea that you can just add fields or not have fields willy-nilly. And I think it runs on this principle. The schemas are pretty awesome until they're not. And when you're creating new projects, a lot of times you have no idea how it's actually going to end up. You start off writing a pet shop application, and then 2 years later, it's a social network for dogs. You just, and I always love cell phones as a great example of something that isn't necessarily used in the way that it was originally envisioned to be used. The number 2 use of a cell phone is text messaging. Are there any guesses of what the number 1 use of a cell phone is? Checking the time. And I think like making phone calls might be number 3, but I think that's even moving on to number 4 after playing Angry Birds. And, so the document principle just accepts this as a reality. Now, the difference between Mongo and Couch. Mongo was built from the ground up to be huge, scalable data sets. That's originally what it was built for. It really wasn't concerned about durability because of an individual data store, because the idea was, well, if one of them crashes, it doesn't matter because it'll just go to a different instance while we reboot that server, and then all will be good. So it does auto sharding and all of this based off this configuration. It has this really simple way to interface through this service called Mongo that sort of handles the routing of all of your requests to the correct server replica sets. But it can be a bear to set up. Couch The one thing I should also mention about Mongo as well is that it does ad hoc queries. If you're familiar with SQL and you like dealing in that sort of environment where you just stick in data and you say, okay, I want to grab this value, and with this query, Mongo's the way to go. Couch, on the other hand, has a very heavy reliance on Mapreduce. And what you do is you run these Mapreduce functions and you create views and you grab data. And I know there's a lot of tools to help facilitate that, but under the covers, that's pretty much what it does. It was originally built to be very, very durable. So what I would say is, if you were building, something like a clinic in Uganda or something, use Couch. Don't try to connect to some Mongo data center somewhere. Just install Couch, because it's very federated in the fact that you'll have an instance of Couch on one device and an instance of Couch on another device and an instance of Couch on another device, and they'll sync up eventually because they have this really amazing master-master replication, which is something that Mongo does not have. Mongo is very master-slave replication-centric. But there have been some attempts to make Couch a lot more a lot more similar to Mongo. And the first attempt was Lounge. I know a lot of people still use Lounge, but it's quickly being overtaken by this, which is called Big Couch. And I would generally recommend Big Couch if you're starting from scratch and you want to create a cluster. But Couch is pretty simple. You start up Couch, and the whole thing is REST-based. It's just REST interactions. It's like you put values in it, and you get values out. You use HTTP URLs. That's where all the data is in, and it stores documents and gives it back and forth. It also has a pretty classy interface. I like Couch's interface. This is Mongo's interface. It's not quite as sexy, but to be honest, don't let this fool you. It's not really as powerful as you would hope, but it's a little more powerful than this. So I threw out the term Mapreduce. I did want to show kind of the idea of what Mapreduce is. This is I believe this is a Mongo Mapreduce. It's in JavaScript. Couch and Mongo are both very heavily JavaScript-centric. If you have a little trouble reading this, then let's look at it in Ruby. Really quickly, actually, I think there's a little more of a Rails kind of a thing, but if you're familiar with the very first line, get all rooms. So imagine you just have a hotel and you have rooms in it, so get them all. Step 2 is called mapping. And when you map, you take an array of some values and you convert them into an array of something else. And that's exactly what this is doing. If you're familiar with the map command, all it's doing is it's just saying, out of all of the rooms, extract the capacity of every room and then put it into this array called caps. And there's this Rails shortcut that you might be much more familiar with, where it's you do map and then ampersand symbol of capacity. And then starting with 0 on reduce, these are all real Ruby functions. They've been there since day one. You can then add the capacity of every single item in the room, every single capacity of every room, and then the result is the total of the capacity out of your entire hotel. Now, you might wonder what the point of doing all of that is when you could have just iterated through and added them together. And it's because of this. It's because you can split that array, that mapped array a little part of each map can be done on a different server, and then they can be reduced on different servers, and then they can be re-reduced, and then finally you end up with one single result. And it works on the idea that it's much cheaper when you have these massive data systems, so these very federated distributed systems. It's cheaper to send the algorithm out to the data than it is to pull the data to you and then perform some function on it. So Mongo versus Couch, we talked about this a bit. I would say again, if you're not familiar and you're not comfortable with Mapreduce, I would try out Mongo first, because you can quickly delve into and I'm not saying that Mongo doesn't support Mapreduce, it does, but that's not really its primary mode. That was something they sort of tacked on at the end. But if you need something that's really durable and you need something that you want to embed, because you can embed couch in anything. I mean, I think there's even a couch for Android, and it works really well. You know, you stick your little couch instance inside of all these cell phones, and then they sync up to the cluster eventually. This is something that Mongo has a very difficult time with. And then what about Raven? And it's .NET, so I'll just, you know. Key value. Key value stores are sort of not very sexy, but I hope you'll see React and Redis will hopefully change your mind on this. React, and I kept talking about the Dynamo implementation by Amazon. React is a very good, faithful implementation of Dynamo with a bunch of other awesome things like vector clocks and things like that for dealing with versioning. Ripple is really good. There's this ORM called Risky. I don't know why it calls it ORM, because ORM stands for Object Relational Mapper, and there's nothing relational about this in any way. But one of the big use cases that people use React is secondary indexes. They use them for caching, second-level caching, and things like sessions. You know, any data just that you would use a normal key value store for. But the nice thing about React is that, you know, again, and this should look familiar. This is just like Big Couch, sort of the same server setup where you have your nodes. This is called a consistent hashing. If you're familiar with this concept, and the idea is that nodes can come up and down, and you don't have to rehash the entire system. Just part of it. I didn't talk about CAP, but the CAP theorem, in a nutshell, is that this idea that your server can be consistent, it can be available, it can be partition tolerant, but you can only have two. It's impossible to make a system that is completely partition tolerant, completely available, and completely consistent. So it can't be beaten. It's just a rule, but it can be tweaked. And what React has sort of pioneered, I don't know if they pioneered, Dynamo pioneered it, but in the open source world, they really took it and ran with it, is this idea that even though it can't be tweaked, it can't be beaten, it can be tweaked. The idea that you can have parts of your system that are really consistent but not as available if it's really important data like billing data or anything like that, and that you can have parts of your system that are highly available, not as consistent, but it's not as important necessarily be like, you know, session information. And you know, we can go over, you know, some of the details on how, and I've got these on the slides. Other key value stores, Memcache is fast. You don't need to use it. Kyoto Cabinet, really durable. It's awesome. You don't need to use it. Redis is amazing. It's fast. It's durable. It's also allows for multiple data structures. I mean, Memcache, Kyoto Cabinet, these things aren't built for multiple data structures. They're built for holding strings. Redis, on the other hand, can do all sorts of things. So you can store lists, you can store data structures like lists where you just keep pushing, so that the first command is called push, rpush, push things into the right. Lunch is the key, and then pizza is the value. So you can start pushing things in. So here, it's like, okay, I want to push in pizza to lunch, I want to push in pie to lunch, I want to push in juice to lunch. And then, you know, give me the range just of the first two, and then it returns it. So you can do almost kind of little subqueries on something, which is pretty powerful. If you've ever used Memcache, there's nothing like it. It can store hashes in the same way. And it can store sets. And what's neat about when it stores sets, it can do set operations. So here, I'm adding 2 people to the set. I'm adding one of the names to a different set. And then the very bottom command is the intersection. I'm saying, give me the intersection of all values that are in both sets. And you can do unions, and you can do, you know, all this, you know, pretty advanced. You can do publish subscribe systems using Redis, where you fire up one client, publish things out, and then you have multiple clients subscribe to that, and then they'll all get the data at the same time. On top of all that, Redis is actually pretty fast. So I've got about 1 minute left to go over graph databases. So Neo4j, FlockDB, GraphDB, you pretty much skip Flock. Neo4j is the one that I highly recommend if you really want to play with it. The idea of a GraphDB is exactly what it sounds. It stores data in graphs. Each of these would be a node, and they link to each other in different ways. This is a graph of the movie The Matrix and how the people are connected to each other. Neo4j is actually fantastic. It's also kind of hard to get a grep on originally because there's many ways to communicate with it. I prefer Gremlin. This is Gremlin. Gremlin is a groovy based language. It's kind of esoteric. But if you don't want to run Java and you want to run Ruby, then there's a REST interface that can execute Ruby scripts in the back end. So if you see the line in the middle that says script, that's actually Groovy, and it's just passing that in to REST. So you can have your cool little Rails app and then just have that Groovy that has Java. You don't need to install Java anywhere else, which, unless you wanted to. FlockDB is fine. I'd check it out. But finally, I would just say just try them all. It's really easy to get started, especially if you have a Mac or something, because you can install every database I talked about here through Peru. So try and run it. Here's just a real quick sheet. The very far left side, far right side is some examples of things that you might want to use these databases for in particular. List of sites, list of papers you should read. And yeah, apparently that's it. But I will have all these slides available for download. We'll have them on the website. And I hope that didn't go too long. I don't know if you guys had any questions, because I think we're actually 4 minutes long, and I don't want to stop anyone from having delicious lunch.
Where are we going to get these slides at on the website?
I'm going to give them to the organizers, and then they'll post them on the website. Also, if you check on my Twitter feed, I'll tweet about it at Kodoroshi. Also, I forgot. I have this amazing T-shirt, so I was going to give it to anyone who asked the best question.
Can I have the shirt?
Yeah. That's good. Yeah, popular vote, you win. That's a question. Are there any other questions, though?
Just a quick one. One of the things in trying to evaluate the databases is a lot of these databases discuss durability, but I kind of question that. For instance, my understanding is VoltDB achieves its speed by just staying in memory.
I'm sorry, what was that?
My understanding about durability, like for VoltDB, is that it just keeps everything in memory, and the whole goal is not to have the entire cluster go down. Do you discuss issues about durability?
Yeah. There will always be a trade-off. The more durable you want something, the slower it's going to be. I mean, that's just, it's like physics. I mean, because you're writing something to disk or storing it in a secondary system. So the more durable you want it, the slower it's going to be. I think Redis is probably one of the purest examples of that, where it just like Volt stores everything in main memory, and then occasionally forks and writes a clone to disk. And you can increase, you can have a sort of a system of record, a write file, where every command is written to this file, and that's definitely more durable. But if you're literally writing every single command to disk, obviously you're not going to get the 100,000 writes a second that you would normally get if you're just dealing with main memory. I will say, as far as durability, Couch is actually probably one of the more durable databases. And I'm not even a Couch fanboy. I work for Mongo HQ, so in the document data store world, I should be a bigger Mongo fan, which I am for certain use cases. But Couch is actually fantastic because of the way that it streams all writes or records. It doesn't do inline updates. It just, when you add more values, it just appends into the end of the file. And what's fantastic about that is if the system crashes in the middle of a write and you boot the system back up, it's just going to look at an incomplete write and be like, oh well, and then it's just going to continue on. So you're not going to ever get corrupted data. but there's, I mean, if you need something super consistent, that's when I would do, something like Postgres or something with some sort of acid locking. Again, one of the things about Volt is, right, you can't be ultra durable because it's very difficult to be consistent. You can't be consistent and available when you're partitioning in the way that you're partitioning in Volt. And I would really love to explain to anybody that's interested in why the cat theorem is the case. I just sort of just declared by fiat that it is a fact. But that's a big 15-minute discussion amongst itself.
Sounds like a great lunch discussion.
Yeah. Right. All right.
All right. Thank you very much, Eric.